is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. If we are to meet our decarbonisation targets, we need to reshape the production, storage and distribution of electricity. Off-road equipment used in construction and other sectors is still very heavily reliant on diesel. The cost of downtime to recharge current electric batteries puts off industrial consumers, as does the short life of the batteries, which then need to be replaced. In many ways, battery technology hasn't developed to keep pace with our growing need for portable power. Storage devices that can balance out the intermittent power produced by renewable sources and our energy demand would be ideal. Identifying viable novel materials to make a new generation of batteries, getting past bottlenecks in lithium supply, set to get even worse as the demand for electric vehicles takes off. Newly designed cooling systems to speed up recharging time and prolong the lives of batteries, and harnessing the power of silicon. Today's episode is looking at breakthroughs in battery design that could affect all of us, supported by EU research funding. Our guests are here to recharge our interest in the often overlooked component of our lives, batteries. Juan Vilatela leads a research group at IMDEA Materials in Madrid. His scientific career is focused on methods for synthesis and assembly of 1D nanomaterials into macroplastics nanotextiles for energy and structural applications. Welcome, Juan.
Hi there. Thank you.
Pekka Peljo is Associate Professor of Materials Engineering at the University of Turku, Finland. He is interested in accelerating the development of the stationary electricity storage technologies for storing wind and solar power, but also in fundamental electrochemistry. Welcome, Pekka.
Thank you. Nice to be here.
Good to have you. Mathieu Desbois is president and one of the co-founders of WattAlps. He has dedicated his career to optimizing energy consumption and emissions in mobile applications, firstly focusing on hybrid cars and then to all kinds of vehicles and machines. His interests lie in electrification, batteries and their optimization. Welcome, Mathieu.
Hello, nice to be here and share about batteries.
Yes, let's talk batteries. Let's talk batteries first of all with Juan now. Juan, silicon has great potential for use in next-generation batteries, and the Synergy project you coordinated tackled the challenges of producing nanostructure silicon that creates a simple, scalable process to result in thick electrodes that are economically feasible. So tell us, what is intriguing the Synergy team now?
Yeah, what we're trying to do and what's intriguing us is how to introduce silicon in lithium-ion batteries. In lithium-ion batteries, the kind that we carry around, because you carry them, they have a different structure and they need to be light, but also they're a bit like if you look at them from on the inside, they're a bit like a sandwich. So they have multiple layers. And one of those layers is a key ingredient is the negative electrode where the charge is stored. And this is called the anode, this negative electrode. Today, we use graphite, and silicon is very important because silicon could store 10 times more charge than graphite.
Wow.
And that's why silicon is considered a key ingredient for the next generation lithium-ion batteries, the third generation.
Well, it sounds absolutely ideal. I mean, everyone likes the idea of their devices running that much longer. So what's holding back the use of silicon? Why aren't we using silicon already?
Yeah. In graphite and other materials, the charge is stored in little holes in the material, in the crystal, to simplify. In silicon, they do mix together and swell. So that can often degrade it a little bit over time. So it means that the challenge is one of the challenges is to make sure that it is preserved, that it doesn't degrade. And the most effective way of doing that is probably to make it very, very small, so small that it's smaller than a crack or a defect. That means making it nano-sized, so super small.
So in fact, making it so small that in fact the degradation can't happen.
Yeah.
Right. Okay. This is fascinating.
That's the general idea. So on the one hand, you want to make it very small so it doesn't degrade, but to make it useful, at least for instance, electric vehicles, we need to make about 10,000 tons of this per year.
Wow.
So there's this conflicting scales. And that is probably, I think, the biggest challenge, to be able to produce it on a large scale with this level of refinement.
And at this particular nano size, yeah. So how did Synergy manage to rise to the challenge of producing nanosilicon?
We develop a process from scratch altogether where we transform a gas that has silicon into a nanotextile. So let me try to go through the steps of this process. So imagine a pipe, a tube, right? which is the reactor. And this can be the pipe, like a big pipe you would see in a pool, for instance, right? So we insert gas in it. So there's gas flowing through it. And we also produce a mist, like a cloud of very tiny particles, catalyst particles that act like seeds. And if we supply a little bit of heat as all of these flows through this pipe, what happens is that the silicon gas transforms into nanowires, so very, very long wires that, because they're flowing through this pipe, they all entangle, a bit like cooked spaghetti. And that's important because it means that at the outlet of this pipe, what you have is a solid material like a textile, almost like office paper. And it means that we have almost a finished electrode already. So this is important, for instance, because you don't make a powder that you need to then mix with solvents and so on. So in one step, you convert a gas or a precursor into a fully finished electrode, and it's nano-sized. But what's very important, and I guess perhaps unique about this method of doing it, is that by doing it as everything runs through this pipe, you can do it super fast. So we can convert the gas into a solid in a couple of seconds.
Wow.
And this is what was a bit of a surprise. And that suggests to us that we can therefore, that this will be cost effective as this is scaled up, because we need to make a large amount, but also that we will be able to produce it very fast, to scale up exponentially, because this is really urgent if you wanted to introduce it in batteries.
You said yourself that it almost took the team by surprise how quickly it happened. That must have been a hell of a moment when you realized. Can you remember that?
Yes, because we were chasing these results, but there was some uncertainty as to whether this could happen or not. And then when the student came and showed it to me, it was just one of those days you will never forget. Especially because, this is going back 5 years, and I just knew that we would be, 5 years down the line, we would be scaling up. And this is what we're doing now. So my student and I founded a company, Flowtech, and for 2 years, it's been industrializing the process, and I'm still optimistic.
Yeah, I'm not surprised. You have every right to be optimistic, indeed. And can you tell me what industries would benefit from this product, from this nanosilicon?
Everywhere where there is a battery that moves, pretty much, to simplify. So of course, one huge area of impact would be electric vehicles, because, if we combine these improvements in the electrode, in the negative electrode, with other improvements in the positive electrode that other people are looking at and so on, and I guess what other people are doing in terms of the pack and so on, I think we can probably double the range of an electric vehicle, and that could really be a trigger point or a tipping point for people to adopt more electric vehicles. And that would have a huge impact on reducing emissions of mobility. So that is a big area of improvement. And another one is, of course, things that fly, like drones used in agriculture, in emergencies, and so on. So everything that moves and needs a battery, and that today we cannot electrify easily.
Excellent. And then therefore also from, as you say, a wider range, which I can imagine actually drones being used in an emergency situation, to know that they had the power to fly much longer would be wonderful. Excellent. So Juan, what caused you to find this interesting? You said that you had a student and you were looking at this. Why did you get into this area of research, actually? I've
been working with nanomaterials ever since I started working on as a scientist, so about 20 years. And I guess I've been through a lot of I've seen the great expectations people have put on nanomaterials, and, they make the news and then everyone forgets about them. And so, those of us still in the field persevere. And there are some examples where nanomaterials are just hugely necessary. A regular battery already has nanomaterials in it. So everyone here today is carrying nanomaterials in their pocket, I think, from what I hear in other electrodes. So they are making a difference, and they will transform the way we move, without a doubt. So that has been a huge motivation for me. And in particular, the fact that this application involves mobility means that we do have a chance now to move the needle and reduce emissions substantially, because this goes to the core of one of the biggest sources of CO2 emissions. So that is a dream come true, to be able to work on a project like this one.
Excellent. No, indeed. Yeah, very good. Any questions at all for Juan, guys? Yeah, Mathieu?
Yeah, a lot of questions. Well, first of all, congratulations on the job already done. And it's impressive. I know everybody's working on silicon, and you said, it's really difficult to manage the swelling of the silicon. And I didn't fully get it how you do it. I understand the way you manufacture the electrode. What I don't understand is how you keep the structure, the mechanical structure of the electrode, and how you make it also the electrical contact between all these very small particles. How do you make sure that you still can, pull the electrons out of them?
I'll try to give a brief answer because this is a very, very good question that would give us enough to grab a coffee together. But because the particles are very long and thin, like wires, they entangle. So this entanglement gives a lot of cohesion to the material. It means that the swelling swelling happens, but they do not disconnect. They do not break apart. If you have powder and like agglomerated powder and it swells, they disconnect. So that's one aspect of it, that these entangled networks, it's a network rather than, like a sintered powder. And the electrical part is super interesting. We're actually looking at the fundamentals of that as we speak. But you can optionally put a bit of conductor, but the truth is you don't really need it because the electrical conductivity of silicon is enough because you don't have a lot of junctions in this network. Again, because they're very long and thin, you need very few wires to bridge electrodes. So the key is that that's the geometry. By going away from spherical particles to very long, thin particles, you get a lot of, you benefit from the properties of the crystal itself.
Thank you. That was an excellent answer. I followed it completely. That was perfect. Thank you. Pekka, did you have a question?
Yeah. So now there's lots of interest on the solid state electrolytes. So are your nanowires actually compatible with that? Or?
It is. And I am fascinated by that prospect because that could be the next big revolution in lithium-ion batteries from what experts like you tell me. And there, the fact that you have a mechanically very robust anode can actually be very beneficial because these electrolytes, these solid electrolytes, they are assembled in radically different ways involving high pressure during fabrication and then during operation. So this mechanical integrity is critical, and we have very good results in the lab from one of my PhD students. So I'm very, very encouraged, but there's just so much to learn on electrolytes.
Sounds like there's so much to learn from all of it, really. Massively complex, portable power, and we use it without even thinking. I mean, people like me, consumers, use it without even thinking. Excellent. Any more questions at all? Oh, Mathieu, you have a question.
Just one little question on where you are in terms of market. Are you close to the market? Do you have already big companies testing your product? Where are you, basically?
We are building a pilot plant to manufacture continuous rolls that we can then, that would directly be shipped to the manufacturers of cells. First, for pre-commercial trials. And we already have some of them make cells, specialty cells, and so the manufacture is going well. I hope we can be making a small packs or enough material to produce packs towards the end of next year.
That's excellent, Juan. That's really round the corner almost. Really great. Excellent stuff. And you're optimistic?
Always.
No alternative really, is there? Very good. Thank you so much. I'm going to turn to Pekka. Pekka, the COMBAT project focused on ways of identifying what new materials could be used in flow batteries using machine learning and high throughput screening. Can you briefly explain how a flow battery works for those of us who've never given it much thought and what the drawbacks are, please?
So in typical batteries, the energy is stored in the electrode, but in flow batteries, you add 2 tanks and you store the energy in the liquid. So if you need more energy storage capacity, we can just take bigger tanks. So this makes these systems quite nice for storing energy for longer duration, like for 4 to 8 hours. But the most commercialized technologies, they are relying on vanadium. Why we need these technologies for energy storage is that if we want to have this renewable energy-based system, we need some ways to keep the lights on when there is no wind or solar, wind or sun. So at the moment, the best option is actually just to pump water uphill and then run it through the turbine. But then this is not very practical in all locations, so that's why we have been looking at these flow batteries. And there, the challenge is that vanadium is not exactly the most abundant material. It's not too rare, but it's in the borderline. So we would like to replace that with some other options.
Right. Okay. And so can you tell me, how are alternative materials currently evaluated and what is Combat doing differently? So there must be other groups of people, researchers interested in finding alternative materials. How does your project Combat differ?
So this sort of traditional approach is very much focused on this, that somebody has an idea or intuition or to try something. And then these materials have to be prepared and purified and characterized. It actually is the right material and then tested. And this takes typically a lot of time. So as an example, this lithium-ion batteries, the development started in the 70s, and then some parts developed in the 80s, and then first commercialization in the 90s.
Right, nearly 20 years then.
Yes.
To go from lithium might be a good idea to lithium-ion batteries.
Yes.
Wow.
So this is very sort of time-consuming.
Yeah.
What we looked at in Combat project was to try to develop tools to accelerate this development. So for new materials, we have quite strict requirements. We have to have the right cell voltage, right solubilities, high enough stability, and preferably also environmentally friendly, so sustainable materials, and also at low cost.
Quite a lot of asks. Huh? Yeah.
Yes, so this is the challenge. So we started to think, how can we use these computational tools that have been developed for the last 10 to 20 years to try to help us to accelerate this development? So in this project, we did the computations to evaluate the redox potential. This is a property that is related to the cell potential or the cell voltage of the battery.
Hang on a second, let me stop you for a second. So the redox potential, what is that? The amount of power that the battery can hold, or the amount of power that the battery will give out?
No, this is the cell voltage is the difference between the two redox potentials.
Okay.
And then the redox potential, the cell voltage then is one of the parameters that defines how much energy you can store and how much power you can get out.
Uh-huh. Right.
Is it too complex? Is
no, that's fine.
Too complicated?
No, that's fine. The amount of power that you can put in and the amount of power you can get out, that's absolutely fine. And that's the redox potential.
It's related to that, yes.
Okay. All right then. And so obviously this is one of the things that you're looking at because that's kind of crucial. You need to know that they can store and emit power and so on. Okay. So you've got these various parameters, all of which absolutely have to be met for the material to be viable as an alternative. And so what are you using? Machine learning or how are you approaching and how do you do the mass screening?
So to use the machine learning, first we have to train the models. And to do this, our collaborators, they calculated redox potentials for roughly 15,000 molecules.
Wow.
And then now that we had this data set, so then we could train the machine to do the predictions. And then finally to end up with a model that we can use to basically predict the redox potential of any organic molecule.
Excellent. Fantastic. So did you identify any potentially interesting molecules that could be investigated further?
So this redox potential is only one of the parameters.
Of course, as we were saying, there's also stability and all of the others as well.
Yes.
But if it doesn't have the redox potential, presumably you don't then carry on investigating it because then if it doesn't have that, it doesn't matter because it won't work. So you start with the redox. Yeah.
So sort of the impact of this is, our outcome is that now we have this one tool. So now when somebody has an idea that this looks like this could be interesting, so they can start by first checking that does it make sense in terms of this redox potential?
To go further. Yeah.
And now we have this tool, so we can also take databases of existing molecules. So there's databases that have, let's say, 2 million molecules.
Wow.
And then screen them.
Excellent.
And then pick those that are in the right range, that this is something that we could study further.
That might have potential.
Yes.
Maybe, yeah, if it meets all the other parameters. But it's a very good way of initially weeding out the ones that clearly can't work so that people can save time not looking at things that are going to be a dead end automatically. Super. What do you hope the outcome of the project's work will be, Pekka?
So now we have this tool that we can predict redox potentials of any organic molecule. So then we hope that this will aid in accelerating this development of these compounds or the materials for the new next generation of batteries.
Mm-hmm. Excellent. And are there any organizations showing interest in using your tool, your idea?
So this is going to be openly accessible to everybody. So there's been some interest already. And
how will people access it? It's going to be online? It's going to be some sort of platform that you have online, or how will you share it?
Yeah. Yes, it's a web application. So you can just go to the web application and then put the structure of the molecule there, and then it gives out the redox potential.
Well, this is fantastic. I think this is excellent. Super. Thank you very much, Pekka. Does anyone have any questions? Yes, please.
Thank you, Pekka. A very fascinating project. I was interested in looking ahead. You're factoring in a lot of the technical challenges with the choosing materials, but I can imagine batteries have multiple use cases with different power and energy requirements. And then on top of that, you have sourcing and other considerations. So how much can these models evolve to take into account all these enormous complexity?
That's a very good question. And actually, we have a project, a continuation project running on this try to actually think of how to manufacture the chemicals. So how to find the synthesis routes and how to use the machine learning. But even the solubility is very difficult to evaluate, and stability is even bigger issue. So
why is the solubility difficult to evaluate?
So there's redox potentials we can evaluate with quite simple computational methods. But then to evaluate the solubility, we need to know what is actually the crystal structure of the solid. So then we can evaluate what's the energy to dissolve the crystal. And it's very difficult to know what's the most stable crystal structure without doing experiments.
I see. It's difficult to identify that without the experimental work that you're trying to get around by having the computerized system.
So if we would have a lot of experimental data, then we could maybe make a machine learning model to try to use that then to evaluate. But to make good models for machine learning, we need a lot of data. So in our case, we had these 15,000 molecules. And now we would need to have these solubility measurements for I would say even more, because then the solubility there's two components in the crystal typically and so on, and it gets very complicated very quickly. So
it does sound immensely complex. Yeah. Super. Thanks very much for the question, Juan. Okay, well, thank you very much, Pekka. I'm going to turn to Mathieu. Mathieu, what else has developed a novel battery for use in off-road mobile machines like those used in the construction sector or mining, for example? Now, we've been talking about electric cars and the storage of energy from renewables and so on, but your work is focused on the extensive needs of the construction industry and other off-road equipment. Can you explain why there is such a need for alternative energy solutions for manufacturers of non-road mobile machinery? What's the demand like?
Yeah, well, first of all, you have to understand that the need for this kind of machines is different than the one you have for cars. And you can see it already today by the engines. The diesel engines are not the same in a construction equipment or in a heavy duty equipment than it is in a car, because these equipment are used much more heavily. They're used like 4 to 8 hours per charge and sometimes several charges per day, whereas a car is only used 1 to 2 hours per day. And maybe once a year twice a year you do a fast charge, because you are doing your big trip of the year. But they are very rarely used intensively. In the heavy duty equipment market, you are using the battery like very intensively with a lot of fast charge, and also you always need to have the same performance. I mean, you always need to have the nominal performance that you need, because you have to do production. I guess most of the people are now aware that a lithium-ion battery loses capacity or loses mileage when it's too cold. For example, if you go in Finland, in the winter, if it's cold and you leave your smartphone on your outside pocket, you lose a lot of energy very quickly. So it's same for all lithium-ion technology.
Right. And of course, much of this machinery is currently dependent on diesel, which is obviously not a particularly environmentally friendly option, indeed.
Yes, for sure.
I suppose also for people managing industrial machines, the downtime necessary for recharging is horribly expensive. I mean, to have a machine that's not available for use because you're recharging.
Yeah, it's true. If you can manage to have sufficient capacity to work for a full day, then you're okay. You can, charge at night. But most applications are so intensive that even with a big battery, you don't have a full day of autonomy. And so in this case, you need to recharge, to do a fast charge during the breaks of the people. And these breaks are not 4 hours or 8 hours.
Unfortunately for the people concerned, yeah.
Yeah, but fortunately for the productivity.
Yeah, no, indeed. And of course, the more charges you do, the less life of the battery. You wear the battery out after a while.
Yeah, and the main concern, well, there are many reasons why fast charging is harming batteries, but the biggest one is the increase of temperature. Temperature increases aging of the battery in an exponential way. It's electrochemistry. It's known. It's the Arrhenius law.
Okay. And so could I ask you, the What Else project was hosted rather by the What Else company.
Yeah.
So what was the solution that you guys came up with?
Yeah, I was coming to it exactly, because you have to control temperature. And we've developed basically what's today the best way of controlling temperature for a lithium-ion battery is we immerse the cells into a dielectric fluid, which is also biodegradable and non-toxic. And we have several patents on how to have an homogeneous temperature inside the battery and how to have an homogeneous circulation of the fluid inside even big battery packs. And this homogeneity allows for longer life and better performance, because this is always the weakest cell in the whole battery system that is limiting the performance of the whole system.
And has this not been done before? I mean, are there current ways of cooling this part of the battery?
Yeah, we are maybe there are 3 companies in the world which are as advanced as us for immersion cooling. I'm not counting the Formula One companies who are just,
Sure, yeah. That's a different application.
This is €1 million for a battery. It's a different application.
Yeah.
But we are 3 companies in the world, and I guess we are the most advanced for immersion cooling with a very modular approach, which can be very easily adapted.
Yeah. Could you explain the modularity? I'm trying to get in my mind's eye, and I'm sure our listeners try as well, to see what it is that you're doing.
Yeah, we're building a battery module like this one. Yeah, you see it's a very handy one. It's a 10-kilogram battery module, and you can stack them together like a Lego brick. It's our Lego brick. And you stack them together to form a Lego brick. And when you stack them, you build your hydraulic circuit. So by stacking them, you build your hydraulic circuit, and it's formed like a heat exchanger. So it's optimized for homogeneous temperature and also very handy modularity. So we can propose basically custom performance, but with Lego bricks that are fully validated, very standard, and that we can very easily integrate into a lot of different applications.
And the fact that they're easily integrated and they're fully standard, I would imagine that also enables companies to use them without having to do so much training of staff and so on.
Exactly. That's why we're targeting this non-road mobile machinery market, because they are not like car manufacturers and do not do 100,000 vehicles per year. When they do several hundreds or several thousands, it's already very good. So they need something very easy to integrate and very modular that they can use on their whole range. And so they cannot use the same battery, the same car battery that you get in the car and put it in a lot of different machines. This is not possible. So they have to have something very modular, and that's why we developed something like this. Yeah.
And the development in itself must have seen some high moments and some low moments. Oh. There must have been times where you thought, yeah, I'm sure. Can you tell us a moment, for example, we had that lovely example from Juan where suddenly they realized that they could do this quickly, which is of course very vital for making it financially feasible. Did you have a eureka moment where actually something worked?
Yeah, well, we had also very difficult moment where it didn't work.
Yes, of course. There's always ups and downs.
Yeah, basically, we launched the 3rd generation of our batteries last year. This is the output of the What Else project. And the 2nd generation of our batteries, we were starting to go to have pilot at customers, and we saw that there was a big problem with the technology. So we had to stop marketing the full 2nd generation of battery, get them back to our plant, go back to the lab, do some fundamental research again to find what was the root cause, try to find a solution. We found the solution, we redeveloped it, and then we validated scale by scale, little by little. It took us 2 years to go to the full certification. And now we have a battery fully validated. We've passed. Yeah, that was impressive. And this is the end of the project, was very impressive. Basically, we went to qualification tests at external labs, and every single test we passed them very, very well. And even abusive testing, where the battery should be dead afterwards, our battery were still functional.
That must have been so satisfying after that really intense 2 years back to the drawing board, and then you managed to pull it off. Bravo.
Yeah, that was fantastic, really.
Yeah, I can imagine. Excellent. And you do have ISO and IEC certifications. I see that as well. That's excellent. And are you finding that industry, you asked that question earlier, now I'm asking it to you, are you finding that industry is showing some interest?
Oh yeah. Now we are in I would say we're in a scale up phase. Like we did little production last year, for prototypes and first demonstrators at our customers. And now they've validated it and they're starting to ramp up production. And the production of this year will be approximately 9 to 10 times the production of last year.
That must be wonderful. Excellent.
Yeah, and next year it will be even bigger. So like at least 3 times what we're doing this year, and hopefully like 5 times. So we'll see.
Perfect.
We'll see. We can keep up the pace, but a lot of market traction. That's very good.
Yeah, that's excellent. I'm so pleased for you. Do we have any questions for Mathieu? Oh, lovely. Lots of questions. I'm going to go with Pekka first and then Juan. Pekka, please.
Sounds very interesting. I was actually wondering how this modularity actually helps with recycling.
Oh, very good question. Thank you. So basically, we've designed the battery modular so that we can easily integrate it into a first high demanding application, but also so that we can take the battery back when they're worn out for the first application and repurpose them for the second application. And we've not designed the mechanical and the hydraulics so that we can do that, but we've also designed the electronics so that we have also a usage history, so we can give a warranty on the second life of the battery. So we've been thinking the whole battery so that to maximize its usage all along the value chain. Because we maximize life, we know we can have a good second life. With our system, we control temperature, so we maximize life, and we can have a very good second life because we've been working in very good conditions for the whole first life.
Excellent. So it's beyond the notion of simply just recycling, but you're actually releasing them back into the system to be used again and again. Very good.
Yeah. When they are at the very end of their life, they are designed to be dismantled easily, safely. That is to say, we have competitors who are, gluing all cells into foam, which is then very difficult to dismantle or disconnect. And all batteries are meant to be very easily dismantled. And what cannot be dismantled can go into a classical crusher for recycling.
Excellent. Yeah, that's excellent. Thank you. Thank you for continuing that. I was also going to mention that, of course, the cooling must mean that you can use more superfast charging as well.
Yeah.
You must be able to charge more quickly.
Yeah, very fast charge. Yeah.
Excellent. Super. Thank you. Juan, you had a question.
Yeah, I was interested in how you deal with different cell designs, because sometimes there are so many, the shape changes, the dimensions, the voltage and so on. How do you deal with that?
Yeah, so before founding WattHelps, me and one of my partner, we designed a lot of batteries with cylindrical cells, prismatic cells, pouch cells, and a lot of different type of cells. And when we decided to go for immersion cooling, we chose the cylindrical shape. So we are with standard cylindrical cells like 18650 or 2170. Why did we choose this? Is because we can have a very compact design, and there is still a natural distance between the cells where you can flow the liquid to cool them down. And since they are very little, it's harder for us to assemble, but the exchange surface to cool down the chemistry is much wider. So we are much better at cooling small cells than at cooling big cells.
Bigger surface area.
Yeah, because bigger surface area. Also, in terms of safety, when there is a problem on one cell, it's not as big a problem as a problem on a big cell. So that's why we chose this format. But the technology is also possible to be done on bigger cells. And the first research project we did at the CEA 10 years ago was with prismatic rigid cells.
Super. I think that answers that very well. Well, I would like to make an observation to all of you. I didn't know very much. I think it's fairly obvious. I didn't know very much about batteries at all. And now I feel I know much more. And I'm also more interested in the subject than I was before I went down this road with you all. And I will not be thinking so lightly every time I recharge my phone. It's good to know that there is new technology down the pipeline. Thank you so very much for your time.
Thank you. Thank you to all of you.
Yeah, thank you.
You're very welcome. It was lovely to have you.
Thank you. It was a pleasure.
Yes, indeed, wasn't it? Thanks very much, Juan. If you've enjoyed this podcast and are interested in the latest scientific research coming out of the EU, have a listen to previous episodes. Follow us on Spotify and Apple Podcasts, and check out the podcast homepage on the Cordis website. We've looked at how AI can help beekeepers and instant on-the-skin tests for TB. In our last 29 episodes, there'll be something there to tweak your curiosity. Perhaps you're interested about what other EU-funded projects are doing to innovate battery design. The Cordis website will give you an insight into the results of projects funded by Horizon 2020 and Horizon Europe that are working in this area. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from string theory to political theory. There is something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.